300 million meters per second. That is the speed of light, the absolute maximum speed anything in reality can reach, and it is embarrassingly, almost insultingly slow for the universe it has to cross. 4 years to our nearest stellar neighbour, 100,000 years to cross the galaxy we actually live in, 2.5 million years to the nearest large galaxy. We have been asking for decades why a universe of 2 trillion galaxies is completely silent. Nobody has answered that question satisfyingly, but the answer might simply be this: the cosmos is not empty. It is a prison. Distance is the wall. Light speed is the lock. Most of the inmates will never see each other, and nobody is getting out. Stay until the end, because tonight we test every single bar and find out just how strong that lock really is. Before we begin, if you genuinely enjoy what I do here, feel free to subscribe, turn your notifications on, and make sure you stay until the very end, because this one is going to sit with you. Now, get cozy and let's ease into it. Part 1. The lie we all believe. Here is something nobody told you in school. The fastest thing in the universe is not fast enough to matter. Let that sit for a second. We have spent centuries celebrating the speed of light as this almost mythical ceiling of reality, the absolute limit, the cosmic speed cap, the thing nothing can ever outrun. And that is all true. Light is the fastest thing that exists. It always will be. Physics guarantees it. And yet, when you actually sit down and do the math, when you measure light not against a bullet or a jet or a rocket, but against the scale of the universe itself, something uncomfortable happens. The number stops looking impressive. It starts looking almost embarrassingly small. And once you see that, once you really internalize it, a question starts forming in the back of your mind that is going to follow you for the rest of this video. If the fastest thing in existence is still this slow relative to the cosmos, then what does that mean for us? What does that mean for anyone out there trying to reach anyone else? The speed of light is 299,792,458 meters per second. That is a defined constant, not a measurement with error bars. In 1983, the International System of Units locked it in permanently by redefining the meter itself in terms of how far light travels in a fixed fraction of a second. So the number is exact, final, settled. And at a human scale, it sounds absolutely staggering. Nearly 300 million meters every single second. That is fast in a way that our brains genuinely cannot picture without help. But here is where the illusion starts cracking. The nearest star to our sun, not our sun, the next one, Proxima Centauri, is 4.24 light-years away. That means light, travelling at 299 million meters per second, without stopping, without slowing down, without taking a single detour, takes 4.24 years to get there. Over 4 years at the maximum speed the universe allows, and Proxima Centauri is our neighbour. It is the closest thing to us outside our own solar system. If the Milky Way were a city, Proxima Centauri would be next door. And light still needs 4 years just to cross that one block. Go bigger. To cross the full diameter of the Milky Way, our own galaxy, the neighbourhood we actually live in, light takes somewhere between 100,000 and 200,000 years, depending on how you measure it. 100,000 years at the speed of a light just to get from one side of home to the other, and then consider Andromeda, the nearest large galaxy to ours, our closest galactic neighbour, visible to the naked eye on a clear night as a faint smudge of light. That smudge is 2.5 million light-years away. The light entering your eye right now when you look at Andromeda left that galaxy 2.5 million years ago. Homo erectus was still figuring out fire when that light began its journey toward your retina. This is what physicists sometimes call the cosmic mismatch. On one side of the equation, you have the speed of light, genuinely, incomprehensibly fast by any human standard. On the other side, you have the scale of the universe, genuinely incomprehensibly large by any human standard. And when you divide one by the other, when you ask how long it takes the fastest thing in existence to cross the distances that actually matter cosmically, the answer is always some version of too long, way too long, embarrassingly, civilization-endingly too long. And this mismatch is not just a travel problem. It is not just about whether humans could ever physically go somewhere. It is about communication. It is about causality. It is about whether any signal, any message, any radio wave, any laser pulse can ever reach from here to there in time to matter. Because light does not just determine how fast we can travel. Light determines how fast information can move, and information moving too slowly means civilizations cannot coordinate, cannot connect, cannot even know each other exists in any meaningful time frame. The speed of light is not just a ceiling on motion, it is the ceiling on relationship itself. There is a man named Enrico Fermi who sat down at a lunch table in Los Alamos in 1950 and asked a question that has haunted science ever since. He looked up at the sky, a universe estimated to contain 2 trillion galaxies, hundreds of billions of stars per galaxy, enormous numbers of planets, and he asked, "Where is everybody?" The universe is old. Life had billions of years to emerge and spread. Intelligent civilizations, if they exist, had more than enough time to make themselves known. So why the silence? Why has nothing ever reached us? Why, in all our listening, have we heard nothing but static? That question has generated decades of theories. Rare Earth, the Great Filter, the Dark Forest, zoo hypotheses, simulation arguments, all of them trying to explain the silence. But what if most of them are unnecessary? What if the answer is sitting right there in the math we just did? What if the silence is not mysterious at all, but simply inevitable, a natural consequence of a universe where the fastest signal possible is still catastrophically slow relative to the distances involved? What if the universe is not empty, but just unreachable? That is the question this video is going to follow. We are going to trace a beam of light from Earth outward, through the solar system, through the interstellar gap, through the galaxy, and out to the edge of the observable universe. And at every step we're going to watch what the speed of light means for connection, for civilization, for any hope of ever knowing we are not alone. Because here is what I think you're going to find by the end. The universe is not empty. It is full. It is almost certainly teeming with stars, planets, chemistry, and probably life of some kind. But it is organized in a very specific and very cruel way. Every civilization, everywhere, is an island. The ocean between islands is made of light years, and the boat, the fastest boat physics allows, moves at the speed of light. And even that boat is far, far too slow. The speed of light is not just a limit. It is a wall, and we are about to find out just how thick that wall really is. Part 2. Fast on Earth, useless in space. Start with something familiar, because this is where intuition goes wrong in the most interesting way. Light circles the entire Earth, the whole circumference, all 40,000 kilometers of it, approximately 7.5 times in a single second. Not per minute, per second. In the time it takes you to blink, light has lapped the planet multiple times. If you fired a laser around the equator right now, it would return to you before your nervous system could even register you had pulled the trigger. At a human scale, at the scale of countries and cities and oceans, light is essentially instantaneous. This is why we do not notice a delay when we turn on a lamp, why fiber optic internet feels real time, why nothing about our everyday experience hints at any limitation in how fast signals travel. Within the bubble of human civilization, light speed is more than sufficient. It feels infinite. And that feeling, that completely reasonable intuition built up over a lifetime of living on one small planet, is exactly what breaks the moment you look up. The sun is approximately 149,600,000 kilometers from Earth. That number is so large it resists comprehension in raw form, so astronomers have a unit for it, 1 astronomical unit, or 1 AU. 1 AU, the distance from Earth to the Sun, and light at 299 million meters per second takes 8 minutes and 20 seconds to cross that one astronomical unit, which means the sunlight landing on your face right now left the sun 8 minutes and 20 seconds ago. You're not seeing the sun as it is, you're seeing the sun as it was 8 minutes ago. That distinction sounds philosophical until you think about what it actually means. We never observe anything in real time, not the sun, not the moon, which we see with a delay of about 1.3 seconds, not the planets, not the stars. Every single observation we make of the universe is an observation of the past. We are always, at every moment, looking backward in time. Light lag is not a curiosity. It is the universal condition of all observation everywhere. This might feel like a minor detail when the delay is 8 minutes. You can live with an 8-minute-old picture of the sun. The sun changes slowly enough that 8 minutes barely matters. But the principle matters enormously because it scales. Every additional distance adds more delay. Every additional delay makes the image older, the information more outdated, the connection more abstract. Follow the sun's family outward and watch what happens. Mercury, the closest planet to the sun, sits at about 0.39 astronomical units. Light crosses from Earth to Mercury in somewhere between 3 minutes and 12 minutes, depending on where each planet is in its orbit. Venus is a similar story. Light travel times between about 2 minutes at closest approach and 14 minutes at furthest. Mars, our most discussed neighbour, our most likely first destination for human expansion, is already a different situation entirely. At its closest to Earth, Mars is about 3 minutes away at light speed. At its furthest, on the opposite side of the Sun, that stretches to about 22 minutes. And this is already where something fundamental starts breaking. Here is a thought experiment that I think puts the whole thing into perspective. Imagine the sun simply vanishes. Right now, this second, it blinks out of existence. What happens? Well, the first thing that happens is nothing. Absolutely nothing changes from our perspective, because the information that the sun has disappeared cannot reach us faster than light. For 8 minutes and 20 seconds, Earth continues exactly as it always has. The sky is bright, the solar panels are working, birds are singing, and then, 8 minutes and 20 seconds after the sun disappeared, the light stops. Darkness falls. And only then does Earth begin to react. But here is the part that really gets under your skin. Gravitational effects also propagate at the speed of light according to general relativity. So for those same 8 minutes, Earth is also still orbiting a gravitational source that no longer exists. For 8 whole minutes, we are orbiting a ghost. Nothing in our instruments would tell us anything was wrong until that wave of information finally arrived. That is what the speed of light actually does at solar system scales. It turns the present into a memory. What you see when you look at the sun is a memory. What you see when you look at Mars is a memory. Your telescope is not a window. It is a time machine pointed backward. The further you look, the older the image. And this is still within our own solar system. This is still inside what astronomers consider our immediate neighbourhood. The implications for anything beyond this, for interstellar distances, for the galaxy, for the universe, those implications are so much worse that they need their own section to even begin unpacking. But before we leave the solar system behind, there is one more implication worth sitting with. The idea that telescopes are time machines is not metaphor. It is physics. When astronomers point the James Webb Space Telescope at a galaxy 13 billion light-years away, they are receiving light that has been travelling for 13 billion years. They are seeing that galaxy as it existed 13 billion years ago. That galaxy today, whatever it looks like right now, is utterly unknown to us, and will remain unknown for 13 billion more years if we wait for the signal. We cannot see the present universe. We can only see layers of its past stacked on top of each other by distance and delay. The universe we think we see is not the universe that exists. It is a fossil record of light. Now think about what that means for the question of connection, for any civilization trying to reach out, trying to listen, trying to find another voice in all that silence. If even the sun, 8 light minutes away, already exists in a past we cannot fully observe. What does connection even mean at the scale of stars? That question starts getting very uncomfortable very fast when you look at what happens the moment you try to control something on another planet. Part 3. The first crack in reality. Mars is close. Cosmically speaking, embarrassingly close. And yet Mars is already enough to break one of the most basic assumptions of modern civilization. The assumption that we can interact with things in real time. The communication delay between Earth and Mars ranges from about 3 minutes at closest approach to about 22 minutes when the two planets are on opposite sides of the Sun. That is not 3 seconds, or a tenth of a second, or the kind of lag you notice on a bad video call. That is 3 to 22 minutes one way. Which means if you send a message to something on Mars, you wait 3 to 22 minutes for it to arrive, and then you wait another 3 to 22 minutes for the response to come back. A simple exchange, one question, one answer, takes anywhere from 6 minutes to 44 minutes of round trip. Ask another question. Add another round trip. Any conversation, any command, any correction operates on a delay that would make it completely unworkable by human standards. NASA knows this firsthand. Every rover that has ever driven across the Martian surface, Sojourner, Spirit, Opportunity, Curiosity, Perseverance, has operated under this exact constraint. Engineers on Earth cannot joystick these rovers in real time. The delay is too long. If a rover is rolling toward a rock that will damage its wheels, and a camera catches it 2 seconds before impact, there is no time to send a stop command and have it arrive before the collision. Instead, rovers are programmed with autonomous hazard avoidance systems. They drive themselves, making their own decisions about obstacles, sending back images and data for engineers to review hours later. The humans are not driving. They are planning routes, uploading instructions, and then waiting. They are managers, not pilots. Mars has already turned direct control into something more like correspondence. This is what you might call command delay civilization, a way of operating where real-time interaction is replaced by pre-programmed instruction sets and patient waiting. It works for a rover on Mars, but now think about scaling that model outward, and watch how quickly everything we consider normal about civilization falls apart. Jupiter is approximately 5.2 astronomical units from the Sun, which puts it somewhere between about 33 and 53 minutes of light travel time from Earth, depending on orbital positions. A signal sent to a probe orbiting Jupiter takes between 33 and 53 minutes to arrive, and the same time again to return. A single round-trip communication takes over an hour. Saturn, at 9.5 astronomical units, stretches that delay to over an hour one way, nearly 2.5 hours round trip. Uranus sits at about 19 astronomical units, like crosses that gap in around 2 hours and 40 minutes. And Neptune, at the outer edge of the planetary solar system, is roughly 30 astronomical units from the Sun, meaning a signal from Earth takes around 4 hours to arrive. 4 hours. You could send a message to Neptune, fly from New York to London, land, and still be waiting for your message to get there. What this means for exploration and coordination is not just inconvenient, it is structurally civilization-altering. When the round-trip communication time between 2 points exceeds the timescale of decisions that need to be made, those 2 points can no longer function as parts of the same system. They have to become independent systems. A base on Neptune would have to make all its own decisions, resolve all its own emergencies, manage all its own resources, because waiting 8 hours for advice from Earth is not a strategy, it is abandonment. The further from Earth you go, the more you're on your own, not by choice, by physics. And this introduces the first major crack in the dream of an extended human civilization. We like to imagine Earth as the centre of a growing interplanetary network, a civilization stretching from here to Mars, to the asteroid belt, to the moons of Jupiter and Saturn. A humanity that expands while remaining connected. But the speed of light makes that unity illusory. Even within our own solar system, the signal delays between planets are already long enough to make real-time coordination impossible. An emergency on a Jupiter colony cannot be responded to from Earth in anything approaching a useful time frame. A political decision on Neptune takes months to negotiate via correspondence. A civilization spread across the solar system is not one civilization communicating across distance. It is multiple separate civilizations, each operating in increasing isolation, connected only by slow, laggy, one-way messages that describe a past that may already have changed by the time they arrive. And again, this is still the solar system. This is still the area around one star. This is the close stuff. The close stuff is already fragmenting us into islands, and we have barely left the driveway. What happens when the distances become interstellar, when the delays stop being hours and start being years? What happens to connection, to communication, to any hope of coordination when a message takes not 4 hours but 4 years just to arrive, with 4 more years to wait for a response? That is what comes next, and it is considerably worse than you are probably imagining. Part 4. The solar system is not small. There is a habit of mind that almost everyone has, and it is not your fault, because it is built directly into every diagram you have ever seen. Open any textbook, any educational poster, any space documentary, and you will find the same image. The sun in the middle, the planets arranged in a neat row or spiral around it, everything scaled to fit on one page or one screen. Mercury close, then Venus, then Earth, Mars, asteroid belt, Jupiter, Saturn, Uranus, Neptune. It looks compact. It looks like a system you could drive across in an afternoon if you had the right vehicle. It looks small. It is not small. It is not even close to small. The distance from the Sun to Jupiter, the 5th planet, which many people intuitively think of as somewhere in the middle of the solar system, is 5.2 astronomical units. 5.2 times the distance from the Earth to the Sun. Light covers that distance in approximately 43 minutes. 43 minutes just to reach Jupiter, which on any standard diagram looks like it is right there, almost neighbourly. Saturn sits at 9.5 astronomical units, about 1 hour and 19 minutes of light travel. Uranus at 19.2 astronomical units stretches the delay to roughly 2 hours and 40 minutes. And then there is Neptune, the outermost planet, at 30 astronomical units from the Sun. A beam of light departing Earth needs roughly 4 hours to arrive at Neptune. 4 hours at the maximum speed the universe permits to reach the edge of our planetary system. If you had a phone that could call Neptune, you would wait 4 hours for the ring, 4 hours for them to answer, and 4 hours for your hello to come back. That is 12 hours for one exchange, 12 hours within our own solar system. The diagrams lied to you. They had to. There is simply no way to draw the solar system to scale on anything a human can hold, and also make the planets visible. If you drew the Sun as a circle 1 centimetre in diameter, Neptune would be over 30 metres away. Not 30 centimetres, 30 metres. The planets themselves would be invisible without a magnifying glass. The emptiness between them would dominate completely. Every diagram of the solar system you have ever seen is a compression artifact, a deliberate distortion that makes it look navigable, traversable, manageable. The real thing is almost entirely empty space, with tiny specks of matter spread across distances that take light hours to bridge. Now bring in exploration. Humanity has sent probes to every planet in the solar system. Voyager 2, launched in 1977, flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It is now the only spacecraft other than Voyager 1 to have entered interstellar space. And when we communicate with Voyager 2 today, a signal takes over 18 hours to make the round trip. 18 hours. For a probe we launched nearly 50 years ago. A probe that has had nearly half a century of constant travel to its name. And it is still close enough that a signal from it reaches us in under a day. This is where lightspeed logistics starts becoming something you feel rather than just understand. Every probe we have ever sent operates under these delays. Every image of Jupiter's storms was transmitted hours after it was captured. Every reading from Saturn's rings was relayed across a gap that light needs over an hour to cross. Every decision NASA makes about these probes is based on data that is already old by the time it arrives, and results in commands that will not execute for hours more. We are running planetary exploration on a time delay that would make any real-time activity impossible. We have adapted to it because we have had to. But adaptation is not the same as overcoming. The delay is still there, structurally, physically, inescapably built into every interaction we have with anything beyond Earth orbit. And even with all of that, the hour-long signal delays to Saturn, the 4-hour wait for Neptune, the 18-hour round trips to our most distant probes, we are still talking about the close part of the solar system, the planetary part, the part on diagrams. Because the solar system does not end at Neptune, not by a long way. It extends outward into a region so large that even light speed delays stop being measured in hours and start becoming something much harder to sit with. The question of just how far the solar system actually reaches and what it means to be at its edge is going to change how you think about what neighbourhood means. Part 5. The Death of Real-Time Civilization. Consider what happens when humans actually try to live somewhere other than Earth. Not visit, not conduct a 90-day mission, actually live there, build infrastructure, raise families, develop economies, make decisions about governance and culture and law. Mars is the most discussed candidate, and the communication delay to Mars, that 3 to 22-minute one-way lag, already creates something that no human society has ever had to manage. A structural, physics-enforced inability to have a real-time conversation with home. Imagine a Mars colony of 10,000 people in the year 2100. They have been there for generations. Their children were born on Mars. They have their own slang, their own rhythm of life adapted to a Martian day that is 37 minutes longer than Earth's. Their own relationship to cold and dust and enclosed spaces and the particular colour of that sky. And when they send a message to Earth, they wait. When Earth responds, they wait again. Any news from home is already between 6 minutes and 44 minutes old before it arrives. Any opinion Earth has about a Mars colony decision arrives after that decision has already been implemented, revised, and possibly abandoned. This is not hypothetical inconvenience. This is the physical mechanism by which cultures diverge. When two populations cannot communicate in real time, they begin making independent decisions at an accelerating rate. They respond to their own local conditions, develop their own local knowledge, build their own local institutions. The feedback loop that keeps them synchronized breaks down, replaced by a slower loop of letters and announcements and news dispatches with multi-minute delays baked in. The psychological distance grows faster than the physical distance suggests it should, because you can emotionally handle being far from home. What changes you is not being able to call home and hear a voice answer in real time. That absence, at first just inconvenient, eventually becomes the definition of a separate world. And this is the mechanism by which the speed of light fractures civilization even within a single solar system. Not through dramatic conflict or political secession, but through the quiet, relentless accumulation of independent decisions made by people who could not wait for approval that was too slow to arrive. A Mars colony is not going to formally declare independence from Earth at some dramatic moment. It is simply going to find, 1 decade at a time, that it has been making its own choices for so long that the concept of coordination with Earth has become largely ceremonial. Now extend this to the outer planets, where the delays are not minutes but hours. A Titan colony, orbiting Saturn, surrounded by nitrogen atmosphere and hydrocarbon lakes, exists in a communication environment where Earth is an hour and a half away in every direction. Decisions happen there without Earth's input because they have to. Emergencies are resolved locally because waiting 3 hours for a round-trip opinion is not an option. And as the separation grows, so does the independence, until what began as Earth's colony has become something with its own identity, its own priorities, its own internal logic, united with Earth in history and species, but separated by physics into something genuinely distinct. This is the first layer of the isolation the speed of light imposes, and we have not left the solar system yet. Within one star system, around one average sun, the physics of signal travel is already sufficient to fragment a civilization into separate islands. And if that is true here, in the tightest possible configuration of inhabited worlds, all orbiting the same star, all within light hours of each other, then what does it mean for the galaxy, where the distances between stars are measured not in light hours but in light years? What does it mean for any dream of a connected interstellar civilization when even the solar system version of that dream is already breaking apart? The answer lies just beyond the edge of the planetary system, in a region most people have never heard of, where the solar system ends and something far more daunting begins. Part 6. The Edge of the Bubble. Most people, if asked where the solar system ends, would say Neptune. It is the last planet. It is the final point on the diagram. Beyond Neptune, the thinking goes, you are in interstellar space. But that is wrong by such an enormous margin that correcting it changes everything about how you think about what it means to leave. Beyond Neptune lies a region called the Kuiper Belt, a disk of icy objects extending from about 30 astronomical units out to maybe 50 astronomical units. That is where Pluto lives, along with thousands of other small cold bodies. But beyond even that, extending from roughly 2,000 astronomical units to somewhere between 50,000 and 100,000 astronomical units, lies the Oort cloud. The Oort cloud is a spherical shell of icy debris, comets in waiting essentially, that surrounds the solar system in every direction like a hollow bubble. It is the outermost structure that is still gravitationally bound to our sun. It is, in the most technical and complete sense, the actual edge of the solar system. 100,000 astronomical units. That is the outer boundary estimate. In light years, that is approximately 1.6 light years. And to put that in perspective, Proxima Centauri, the nearest star, is 4.24 light years away. That means the solar system, measured from its true outer boundary, extends more than a third of the way to the nearest star. Our front yard reaches a third of the way to the neighbour's house. Now bring in Voyager 1, humanity's most distant spacecraft, the object we have sent furthest from Earth in the nearly 70 years of the space age. Voyager 1 was launched in September 1977. As of right now, it is roughly 23 billion kilometres from the Sun, travelling at approximately 17 kilometres per second. 17 kilometres per second sounds extraordinary. It is, by any human standard, an almost incomprehensible velocity. And Voyager 1 has been maintaining that speed for nearly 50 years. Yet it has not come close to leaving the solar system in the complete sense. It crossed the heliopause, the boundary of the solar wind, in 2012. But the Oort cloud is still ahead of it, thousands of astronomical units away. At Voyager 1's current speed, it would take roughly 300 years just to reach the inner edge of the Oort cloud, and around 30,000 years to cross through the Oort cloud entirely and enter the true interstellar medium, 30,000 years to exit our own solar system, travelling at 17 kilometres per second, non-stop, having started nearly 50 years ago. Now compare that to light. Light crosses the Oort cloud, all 100,000 astronomical units of it, in about 1.6 years. Our fastest spacecraft, after almost 50 years of travel, is not even close to where light would be after less than 2 years. The gap between what we can build and what physics demands for any meaningful interstellar travel is not a gap that engineering optimism can easily bridge. It is a chasm of such proportions that it rewrites the entire conversation about what it means to explore beyond our star. And sitting with that chasm for a moment is worth it, because we are still talking about the solar system, our star's gravitational domain, the home system, the place we live, and even leaving home, truly leaving, in the most complete physical sense, is a 30,000-year project at our current best speed. We have not even stepped off the porch. We have not reached the end of the driveway. Humanity, as a spacefaring species, is still essentially indoors. The door is 1.6 light-years thick. What lies beyond it is a darkness of a different order entirely. Part 7. The Nearest Star Problem. Proxima Centauri is 4.24 light-years from Earth. Write that down somewhere. Let it become real in your mind, because it is the number everything else scales from. 4.24 light-years. That is the nearest star. Not the nearest interesting star. Not the nearest star with confirmed planets. The nearest star, full stop. The closest other sun to our own. The first rung on any ladder that leads to anywhere else in the galaxy. And light. Not a rocket, not a probe, not anything we could build, but light itself, the fastest thing physics allows, takes 4 years and about 3 months to make the trip. What does that mean for communication? It means that if you sent a radio signal to Proxima Centauri right now, today, this moment, it would arrive in 4.24 years, and if someone there received it and responded immediately, their reply would arrive back at Earth in another 4.24 years. The minimum round-trip time for any exchange of information between Earth and the nearest star is 8.5 years. Not 8.5 hours, 8.5 years. A conversation, a single exchange of one message and one response, 8.5 years minimum. If you were 20 years old when you sent your message, you would be 28.5 before the response arrived, assuming anyone was there to respond at all. And if you had a follow-up question, you would be 37 before that answer came back. This is what you might call generational messaging, communication on timescales that exceed the length of careers, that span significant portions of human lifetimes, that make any back-and-forth dialogue essentially impossible in any normal sense of the word. It is not conversation. It is correspondence so slow that the word correspondence barely applies. It is more like leaving a note in a time capsule and hoping someone opens it a decade from now and leaves their own capsule in response. The stars in our immediate stellar neighbourhood include Alpha Centauri A and B, which orbit each other about 4.37 light-years away, barely further than Proxima, which is actually gravitationally associated with them as a triple system. Barnard's star sits at about 5.96 light-years. Wolf 359, made famous by a Star Trek battle, is 7.78 light-years. Sirius, the brightest star in our night sky, is 8.6 light-years away. These are the close ones, the immediate neighbourhood, and the communication delays to these neighbours range from about 8.5 years to 17 years for a single exchange. When you look up at the night sky, here is something worth keeping in mind. The stars you can see are, in an astronomical sense, the ones practically next door. The faint ones, the ones your eye can barely make out, are hundreds of light-years away. The majority of the Milky Way stars are completely invisible to the naked eye, because they are simply too far. And even the close ones, the bright ones, the famous ones, exist in a communication regime so slow that coordinating anything with them is impossible in human terms. Consider humanity's radio bubble. We have been broadcasting radio signals strong enough to potentially be detectable from space since roughly the early 20th century. Guglielmo Marconi's first transatlantic transmission was in 1901. So our radio bubble, the sphere of electromagnetic signals propagating outward from Earth in every direction, has a radius of about 125 light-years right now. That sounds like a lot, 125 light-years, but the Milky Way is 100,000 to 200,000 light-years across. Our signal bubble covers an area representing perhaps 1% of the galaxy's diameter. Most stars in the Milky Way have not received a single signal from Earth. Not one. They do not know we exist, not because we have been silent, but because our signals have not arrived yet. We have been broadcasting for over a century, and the information has barely left the front porch on galactic scales. And if there is a civilization around a star 300 light-years away, which is still extremely close on galactic terms, they are looking at a quiet Earth. No signals, no television, no radar, no evidence of technology. Whatever they can observe of Earth from that distance, they are seeing Earth as it was 300 years ago, in the early 1700s, before industrialization, before radio, before any technological signature we would recognize as civilization. We are invisible to most of the galaxy not because we are hiding, but because the light carrying our existence has not gotten there yet. That is the other side of the same coin. We are looking for signals from civilizations that may have broadcast centuries or millennia ago, whose signals are still en route to us. They may be looking for signals from us that will not arrive for centuries more. The timing problem alone, two civilizations needing to exist simultaneously, broadcast simultaneously, and happen to be listening in the right direction at the right time is staggering. And every year that passes without contact does not mean no one is out there. It may simply mean the signals have not crossed the gap yet. The silence we hear is not necessarily the silence of an empty universe. It may be the silence of a universe where everything is speaking, but nothing has arrived. Part 8. The futility of travel. If signals are too slow to be useful at interstellar distances, what about physical travel? What if, instead of waiting 8.5 years for a message to make a round trip to Proxima Centauri, we just went there, sent a probe, sent a ship, something physical, with instruments, with perhaps a transmitter to beam back data once it arrives? Voyager 1, as we established, is moving at about 17 kilometers per second. To put that in interstellar terms, at that speed, reaching Proxima Centauri would take approximately 73,000 years. Not a practical plan. But Voyager was never designed for interstellar travel. It was a planetary mission that happened to leave the solar system. What if we actually tried? The most ambitious near-term proposal for interstellar travel is Breakthrough Starshot, a project backed by a serious investment of $100 million, announced in 2016, designed to accelerate a fleet of gram-scale spacecraft using powerful ground-based lasers. The target speed, 20% of the speed of light. At that velocity, a probe could reach Alpha Centauri in roughly 20 years of travel time. 20 years is not nothing, but it is within the span of a scientific career, within a generation, within a time frame that feels human rather than geological. This sounds like progress. This sounds like a way out. But notice what happens even if it works perfectly. You launch a probe at 20% light speed. 20 years later it arrives at Alpha Centauri. It takes pictures. It measures magnetic fields, scans for atmospheric signatures on any planets, collects data, and then it sends that data back at the speed of light, which takes another 4.37 years to arrive at Earth. So the absolute best case, launch, 20-year travel, data collection, transmission, is roughly 24 or 25 years before the first return data reaches Earth. And that data describes a moment 24 years in the past by the time it is being analysed. Every follow-up question you have generates another data request that takes another 4 years to arrive and another 4 years to answer. You're not exploring in real time. You're sending letters to a probe that wrote back in the past and will not receive your next question for years. The asymmetry is brutal. Exploration becomes archaeology. You're always studying something that has already happened, sending instructions for a situation that has already evolved, making decisions based on data that is already old. The further the probe, the worse this gets. A probe sent to a star 10 light-years away operates on a 20-year lag. A probe at 50 light-years sends back information that is half a century out of date. The universe is structured so that the more you reach out, the less you can interact with what you find. This is the core of the isolation problem, not just the travel time, not just the signal delay, but the combination of both, creating an exploration environment where real-time interaction, the kind of exploration that actually builds understanding and relationship and connection, is physically impossible at interstellar scales. The speed of light is not just a wall between civilizations, it is a wall between any civilization and genuine knowledge of what lies beyond it. Part 9. The Civilization Killer. Here is a thought that does not get discussed enough in the conversation about space exploration and long-term human survival. We frame the challenge of reaching other stars almost entirely as an engineering problem. Build a faster ship, develop better propulsion, find a way to keep people alive for journeys that last longer than any human life, solve the problems one by one, throw enough money and genius at it, and eventually you get there. That is the implicit assumption underneath almost every serious conversation about interstellar travel. The problems are hard, yes. The timelines are long, yes. But they are engineering problems, and engineering problems, given enough time and resources, get solved. But the speed of light imposes a challenge that is not an engineering problem. It never was. It is a survival probability problem, and once you see it that way, the entire conversation shifts into something considerably darker and considerably more urgent than most people are comfortable sitting with. Consider the timeline of travel to even the nearest stars at any plausible speed we could realistically achieve or even theoretically propose. The fastest system we have seriously put forward, Breakthrough Starshot's laser sail probes, designed to be accelerated by powerful ground-based lasers to roughly 20% of the speed of light, takes approximately 20 years to reach Alpha Centauri. 20 years. That sounds almost manageable. Within a career, within a generation. A crewed mission at that same speed would also take 20 years, assuming we could somehow solve the enormous biological and engineering challenges of keeping human beings alive and functional inside a vessel travelling at 1/5 the speed of light, which is itself a set of problems we're nowhere near solving. But set that aside. 20 years sounds like progress, except that current technology is not anywhere near 20% light speed, not even close. The gap between what Breakthrough Starshot proposes and what we can actually build today is so large it is almost not worth comparing them directly. Even at 1% of the speed of light, a velocity that would require energy inputs so vast they exceed our current global energy production by orders of magnitude, the journey to Alpha Centauri takes over 400 years, 4 centuries of travel at 1% light speed, which we cannot achieve. A generation ship travelling at any speed we could realistically build toward today takes not centuries but thousands of years to reach the nearest star. Thousands of years of continuous, uninterrupted, flawless operation, of biological continuity across dozens of human generations, of social cohesion among people who are born on a ship, will die on a ship, and will never once in their entire lives see a planetary surface. And during all of that time, all those centuries, all those millennia of crawling across the interstellar gap, Earth continues to exist. Earth continues to evolve. Earth continues to face its own risks, on its own timeline, completely indifferent to the tiny vessel of humans inching through the darkness between stars. And this is where the real problem lives, because civilizations are not stable, species are not permanent. These are not pessimistic statements. They are the straightforward conclusions of 4.5 billion years of Earth's geological and biological history. Earth has experienced 5 major mass extinctions, events so catastrophically comprehensive that the majority of species alive at the time simply ceased to exist. The Permian extinction, the worst of them, eliminated something like 96% of all marine species and 70% of terrestrial vertebrate species. Not a bad century, not a difficult era, 96% gone. The planet essentially started over. Supervolcanic eruptions have come close to ending human history before civilization ever had a chance to begin. The Toba catastrophe, roughly 74,000 years ago, may have reduced the entire human population to somewhere between 3,000 and 10,000 individuals. We came that close to simply not continuing. One geological event, and the entire experiment ends before it starts. Asteroid impacts large enough to cause civilization-ending damage occur on timescales of tens of millions of years, which sounds safely remote until you remember that we have only been technological for perhaps a few hundred years, and tens of millions of years is a timescale on which even our most optimistic interstellar projections are just a brief flicker. And that is before we even get to the self-inflicted risks. Pandemics, nuclear conflict, engineered pathogens, climate collapse, artificial intelligence systems that develop in ways we cannot predict or control. Each of these adds its own probability weight to the ledger of things that could end the experiment before the backup is established. Over geological timescales, any civilization has a non-zero probability of collapse that, when you integrate it across enough time, approaches something uncomfortably close to certainty. Not because civilizations are stupid or self-destructive by nature, simply because nothing lasts forever and the universe offers an enormous number of ways to fail. This is where the speed of light stops being a communication inconvenience and becomes something considerably darker. It is a hard constraint on how quickly a civilization can distribute itself widely enough to become extinction-proof. And extinction-proof is the key concept here. If you can reach other star systems in decades, real decades, not centuries, not millennia, you can establish self-sustaining colonies before any single catastrophic event can end everything in one stroke. Earth dies, whether from an asteroid or a supervolcano or war or something we have not imagined yet, but humanity survives at Proxima Centauri, at Barnard's star, at Epsilon Eridani. The backup exists. The experiment continues somewhere else while Earth recovers or does not recover. The species does not end because one planet had a bad century. But if reaching those stars takes thousands of years, the math changes completely. You have thousands of years of total vulnerability, a single point of failure, one planet, one civilization, one catastrophic event away from permanent silence, during which the backup is not yet established and cannot yet be established because the ship has not arrived. This window, the period in which a civilization is technologically sophisticated enough to attempt interstellar migration, but has not yet succeeded in planting a self-sustaining colony anywhere else, is at realistic travel speeds an extraordinarily dangerous time to be alive. We're in that window right now. We've been in it since we developed the technological capacity to think seriously about leaving, and we will remain in it for a very long time. Now let me give you the specific scenario that genuinely haunts me. Because abstract probability is one thing, a human story is another. Imagine a colony ship launched from Earth 3,000 years from now. Humanity has had 3 more millennia to develop technology, accumulate knowledge, solve problems we cannot currently imagine. And they launch. The destination is a star 20 light-years distant, not far on galactic scales, practically next door, and the ship, equipped with the best propulsion technology 3,000 years of progress can produce, will take approximately 500 years to arrive. 500 years. The people who board that ship will not land. Their children will not land. Their grandchildren will not land. Generation after generation will be born aboard the vessel, will live their entire lives in its corridors and compartments, will grow old and die in the darkness between stars, having never seen a sky that was not a viewport, and their great-great-great-grandchildren will finally land on something solid, under an alien sun, and begin the work of building. They set up. They begin construction. They send a signal back to Earth. We made it. We are here. The planet is viable. Everything worked. And then they wait. 20 years for that signal to travel back across the gap. 20 more years for Earth's response to arrive. 40 years minimum for a single exchange. And when Earth's response finally comes, it arrives from whatever civilization Earth has become in the 540 years since the ship departed. Whatever it has endured. Whatever it has survived or failed to survive. Whatever it has become culturally, politically, biologically, a civilization 5 centuries removed from the one that built the ship and said goodbye at the launch. And then consider the silent scenario, the one that really sits with you at 3 a.m. What if no response comes? What if after 40 years of waiting, and then 50, and then 60, there is only static? What do the colonists conclude? Has Earth simply gone quiet? Technologically evolved beyond radio, shifted to some communication method the colonists cannot receive? Is the transmitter on their end damaged? Is there a natural interference source between the stars that is blocking the signal? Or is civilization simply gone? Did something happen in those 500 years of travel that ended everything back home while the ship was crossing the dark? The speed of light makes it impossible to know, impossible to investigate, impossible to resolve in any time frame that matters for the decisions that need to be made right now, on a new world, by people who have only each other and an ocean of silence between them and everything they came from. This is isolation at a depth that is genuinely difficult to hold in your mind all at once. Not isolated by inconvenience, not isolated by distance in the way that moving to another continent feels distant. Isolated by time, isolated by physics, isolated in ways that make the entire concept of belonging to a large civilization, of being part of something that extends beyond your small colony on a cold rock under an unfamiliar star, almost entirely abstract. A story people tell their children about a place called Earth that may or may not still exist, that sent them here 5 centuries ago and has not been heard from since. And this same scenario, this exact texture of isolation, scaled across billions of stars and trillions of years of possible evolutionary history, may be what the universe looks like everywhere. Not just here, everywhere. Civilizations that emerge from their oceans and their primordial chemistry, that develop fire and language and science and ships, that expand as far as their physics allows, and are then severed, not by war, not by disaster, not by choice, but by the fundamental speed limit of reality, separated from each other by an ocean that even light crosses slowly, not destroyed, not hiding, not silent by choice, just disconnected, permanently and completely, by the one law of physics that nothing has ever broken. Islands that cannot reach each other, an ocean made of light years, and the fastest boat physics allows is still far, far too slow. And now we scale up one more time. Because everything we have discussed so far, the colony ships, the survival windows, the 40-year silences, has been about individual stars, individual civilizations, the small scale. The galaxy contains between 100 and 400 billion of them, and what happens when you apply this same logic to that number is where this story goes somewhere it does not easily come back from. Part 10. The Milky Way Barrier. The Milky Way is somewhere between 100,000 and 200,000 light-years across. There is genuine scientific debate about the precise measurement, and that uncertainty is itself worth pausing on for a moment, because the reason we do not know exactly how large our own galaxy is tells you something important about our situation. Mapping the Milky Way from inside it is like trying to draw the complete floor plan of your house while locked in one room with no windows, no blueprint, and no way to walk the halls. We are embedded in the thing we are trying to measure, surrounded by gas and dust and 100 billion stars that obscure our view in every direction. We're doing our best from a single vantage point somewhere out on one of the spiral arms, peering inward and outward simultaneously, trying to reconstruct the shape of something we cannot step outside of. The rough number, call it 100,000 light-years, is large enough to make every point that follows, but hold on to that image of being locked inside the thing you are trying to understand. It comes back. At the centre of the Milky Way, approximately 26,000 light-years from where we're sitting right now, there is a supermassive black hole called Sagittarius A star. It has a mass of roughly 4 million times that of our Sun. 4 million suns compressed into a single gravitational point at the heart of our galaxy, surrounded by dense clouds of gas and dust and stars packed so tightly that the night sky from a planet near the galactic centre would contain thousands of stars visible to the naked eye, a sky so crowded with light it would look nothing like ours. We know it is there. We have observed stars orbiting it directly, watched them swing around the invisible mass at the centre, in tight, fast ellipses that confirm something enormous is sitting there. Sagittarius A star is as real and as confirmed as anything in modern astronomy. And if you wanted to send it a message, not to the black hole itself, obviously, but to any civilization that might exist anywhere near the galactic centre and receive a response, you would wait 52,000 years for the round trip. Just let that number sit for a second before we move on. 52,000 years. Not 52,000 days, not 52,000 months, 52,000 years. That is the minimum time any exchange of information with the centre of our own galaxy requires, assuming both parties respond instantly and the signals travel at the maximum speed the universe permits, which is the speed of light. Now compare that to something human. Anatomically modern Homo sapiens, people with our brain size, our cognitive architecture, our capacity for complex abstract thought, have existed for somewhere between 200,000 and 300,000 years, depending on which fossil evidence you use. But the things we recognize as distinctly, unmistakably human, structured language, representational art, ritual burial, long-distance trade networks, the accumulated transmission of knowledge across generations, those behaviours appear in the archaeological record starting roughly 50,000 years ago. The cave paintings at Lascaux, the carved figurines of the Aurignacian culture, the evidence of minds that were not just surviving but meaning-making, storytelling, world-interpreting. That is our cultural history. All of it. Every civilization, every language, every religion, every war, every scientific discovery, every piece of music ever composed, every building ever constructed, every book ever written. All of it fits inside approximately 50,000 years. A round-trip message to the centre of our own galaxy takes longer than that. Longer than the entire span of recognisable human culture. You could rerun all of human history, from the first cave painting to whatever we become next, and the signal would still be travelling, and that is to the centre. The far edge of the Milky Way is 100,000 light-years away. A message to the rim and back takes 200,000 years, more than the total time our species has existed in any form, more time than separates us from the common ancestor we share with Neanderthals. The galaxy is not large in a way that travel brochures prepare you for. It is large in a way that erases the concept of communication entirely. So what does any of this mean for the dream of a galactic civilization? For the science fiction vision of a connected network of worlds, an interstellar federation of species sharing knowledge and culture and resources across the galaxy? What does it mean for any empire of stars that might theoretically exist, any collective intelligence trying to maintain coherence across the full width of the Milky Way? It means, essentially, that it cannot exist. Not in any form we would recognize as a civilization, not as a coordinated system, not as anything with shared governance, shared decision-making, shared identity in any meaningful real-time sense. The communication lag alone defeats the concept before it can even get started. Think about what it means to govern something, to coordinate something, to maintain any kind of coherent collective across distances where your fastest possible message takes 100,000 years to arrive. Any decision made at the galactic centre reaches the rim 100,000 years after it was made, arriving in a political, cultural, technological and physical environment that has had 100,000 years to become something utterly unrecognisable. The civilization that sent the original message might not exist anymore. Its language has almost certainly evolved beyond recognition. Consider how different English is from what was spoken a mere 1,000 years ago, and then multiply that by 100. Its concerns, its values, its entire framework for understanding reality, ancient history, its instructions, arriving after all that time, might be not just irrelevant but literally incomprehensible to whoever receives them. A galactic empire is not hard to build because of logistics. It is impossible to build because of physics. The speed of light makes coherent coordination across galactic distances a contradiction in terms. You cannot have a civilization that spans 100,000 light-years because civilization, by definition, requires some form of meaningful communication, and meaningful communication requires that your messages arrive in an era that still recognizes what you are trying to say. The Milky Way contains somewhere between 100 billion and 400 billion stars. That number is almost certainly an underestimate given ongoing survey improvements, but even the conservative end of that range is staggering. And we now know from the Kepler Space Telescope's planet hunting mission and everything that has followed from it that most stars have planets, not some stars, Not many stars, most stars. The universe is profligate with planets in a way that surprised even optimistic astronomers when the data started coming in. Rocky planets in habitable zones, the so-called Goldilocks region, where liquid water can exist on a surface, are common enough that even conservative estimates suggest billions of potentially interesting locations in our galaxy alone. The sheer density of possibility is almost overwhelming. But here is the thing about density. Density is not connectivity. Having 400 billion stars in one galaxy does not mean those stars can talk to each other. It does not mean information flows between them, that civilizations know about each other, that any network of awareness or relationship exists across that incredible number of suns. The light travel times between them are the thing that matters, and those times guarantee that any meaningful exchange of information between star systems operates on timescales that dwarf civilizations, that exceed species' lifespans, that make the word exchange almost philosophically incoherent. Here is a thought experiment that I think puts the whole thing into perspective in a way that is difficult to shake once you have sat with it. Imagine a civilization somewhere on the far side of the galaxy, near the rim, maybe 30,000 light-years further from the galactic center than we are. That is 100,000 years more technologically advanced than us. 100,000 years. They discovered physics when our ancestors were still painting on cave walls. They have had 100,000 extra years of scientific development, of engineering progress, of whatever intellectual and technological growth a civilization with that kind of head start looks like. And they have been broadcasting. For all of that time, or at least for some significant portion of it, they have been sending signals outward into the galaxy, announcing their existence, sharing their knowledge, reaching out. Those signals have been travelling at the speed of light for 100,000 years, which means they have covered 100,000 light-years in every direction, which means, given the size of the Milky Way, they have reached most of the galaxy by now. In principle, their signals are washing over Earth right now, or have been at some point in the past, or will be at some point in the future. But here is what those signals actually contain. They describe a civilization as it existed 100,000 years ago, before anatomically modern humans existed in any form. Whatever that civilization was broadcasting about their science, their culture, their understanding of the universe, it is a message from a society that predates our species entirely. And our response to those signals, if we ever detect them and recognize them and send something back, will arrive at their home star 100,000 years from now, describing us as we are today. To whatever that civilization has become after another 100,000 years of development, we would be the primitive ones. Our message would be the ancient artifact. Our questions would be answered, if they are answered at all, for ears that no longer exist in any form we would recognize. No handshake, no dialogue, no relationship in any sense that the word relationship normally implies. Just signals crossing in an emptiness too vast for any exchange to feel like contact. Two civilizations talking past each other across time, messages arriving in the wrong era, questions posed to a version of the listener that has long since ceased to exist. It is not communication. It is archaeology happening in both directions simultaneously, each civilization excavating the fossilized signals of the other, trying to reconstruct something living from evidence that was already ancient before it arrived. And this specific, inescapable, physics-enforced reality, is the moment where the Fermi paradox stops being a mystery and starts being a logical consequence. Enrico Fermi's question, posed at a lunch table in 1950 and never satisfactorily answered since, was simple. Where is everybody? The universe is old. It is enormous. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars. Life had billions of years to emerge and spread. Intelligent civilizations, if they exist at all, had more than enough time to make themselves impossible to ignore. So why the silence? Why, in all our listening, have we heard nothing? The answer the speed of light provides is not dramatic. It is not a great filter killing civilizations before they can broadcast. It is not a dark forest of predatory civilizations enforcing silence through fear. It is not a zoo of advanced beings watching us from careful distance. It is simply this: the signals proving the existence of other civilizations either have not arrived yet, or arrived so long ago that we did not recognize them, or will not arrive for thousands or millions of years more. The silence is not the universe telling us we are alone. It is the universe operating exactly as the physics predicts it should. The speed of light makes alone the default condition, not the exception, not the tragedy, the default, the expected outcome, the thing that is guaranteed to be true for every civilization everywhere, regardless of how common or rare life turns out to be. The galaxy is full of stars. It may be full of life, and it is, for all practical purposes, completely and permanently disconnected from itself. Every civilization an island, every signal a message in a bottle thrown into an ocean so large that finding the shore it came from is essentially impossible. Every attempt at contact an act of faith in a physics that offers no guarantees and no shortcuts and no exceptions. The silence is not a mystery waiting to be solved. The silence is the answer. Part 11. The Fermi Paradox Reframed. Enrico Fermi was a physicist of extraordinary clarity, the kind of thinker who could cut through layers of complexity with a single, almost casual question. In the summer of 1950, during a lunch conversation at Los Alamos, he did exactly that. Surrounded by colleagues, in the middle of a discussion about extraterrestrial life and interstellar travel, he paused and asked what has since become one of the most enduring questions in science. If the universe is as vast, as old, and as fertile for life as it appears, where is everybody? That question, now known as the Fermi Paradox, has echoed for decades. It seems simple on the surface, but it carries a quiet weight that becomes harder to ignore the more we learn about the cosmos. We now know that our galaxy alone contains hundreds of billions of stars. Many of those stars host planets. A significant fraction of those planets exist in regions where liquid water could exist. Multiply that by the estimated trillions of galaxies in the observable universe, and the numbers become staggering. Statistically, life should not be rare. Intelligence should not be rare. Technological civilization should not be rare. And yet, the sky is silent. Over the years, dozens of explanations have been proposed to resolve this contradiction. Some are optimistic, suggesting that intelligent life is simply rare. Perhaps Earth is an extraordinary accident. Others are darker. Some propose that civilizations inevitably destroy themselves before they can spread beyond their home systems. Others suggest that advanced civilizations deliberately remain silent, hiding in what has been called a dark forest, avoiding detection to prevent potential threats. There are hypotheses that we are being observed but deliberately ignored, as if we are part of some kind of cosmic preserve. There are even suggestions that life itself is common, but intelligence is a fluke that almost never arises. All of these ideas share a common assumption. They assume that the silence requires explanation in terms of behavior, what civilizations choose to do or fail to do. They assume that somewhere out there are beings making decisions that determine whether we hear from them. But there is another possibility, a quieter, more unsettling one. What if the silence has nothing to do with choice at all? What if it is not a sociological problem but a physical one? What if the silence is exactly what we should expect given the laws of the universe? Jill Tarter, one of the most influential figures in the search for extraterrestrial intelligence, or SETI, offered an analogy that reframes the problem in a way that is both humbling and revealing. She pointed out that, despite decades of searching, humanity has explored only an infinitesimal fraction of the possible search space for extraterrestrial signals. We have scanned limited portions of the sky over relatively short periods of time, using instruments sensitive to only certain frequencies and signal types. Her comparison is simple. It is like dipping a single glass into the ocean, finding no fish in it, and concluding that the ocean contains no life. The implication is obvious. but often overlooked. The absence of evidence is not evidence of absence. It is evidence of how little we have looked. But even this analogy, powerful as it is, only scratches the surface of the problem, because it assumes that if we searched more, longer, wider, deeper, we might eventually find something. It assumes that signals are out there, waiting to be discovered if only we refine our methods. What it does not fully confront is the brutal reality of what happens to signals as they cross the vast distances between stars. Radio waves, like all electromagnetic radiation, obey the inverse square law. As they travel outward, they spread. The same energy that begins concentrated at the source becomes diluted over an ever-expanding sphere. Double the distance and the signal strength drops by a factor of 4. Increase the distance by thousands of light years and the signal becomes vanishingly weak. What begins as a clear, structured transmission can degrade into something indistinguishable from background noise. Now layer in the environment of space itself. The galaxy is not silent in a literal sense. It is filled with natural radio emissions, pulsars, quasars, stellar flares, cosmic microwave background radiation. Against this backdrop, a faint artificial signal arriving from across the galaxy may not stand out at all. It may arrive as nothing more than a statistical fluctuation, buried in noise, impossible to recognize as intentional. Even if a civilization were broadcasting continuously, and even if their signal were initially powerful, by the time it reached us it might be effectively invisible. And the reverse is equally true. Humanity has been producing detectable radio signals for roughly a century. That means our radio bubble, the region of space reached by our transmissions, is about 100 light-years in radius. In a galaxy that spans 100,000 light-years, that is effectively nothing. Most of the Milky Way has not had time to receive even the faintest whisper of our existence. Then there is the problem of timing. For two civilizations to detect each other, they must not only exist, they must exist at the same time, within overlapping windows of technological capability. One must be transmitting while the other is listening, using compatible methods, at the right frequencies, pointed in the right direction. If one civilization rises and falls over the course of 10,000 years, a blink on cosmic timescales, and another emerges 1,000,000 years later, their signals will never overlap. They will pass through the same region of space separated not just by distance, but by time. This alone makes detection unlikely. But the deeper issue, the one that reshapes the entire question, is the constraint imposed by the speed of light itself. Because even if the galaxy were filled with civilizations, all transmitting signals in every direction, what we would observe would not be a synchronized chorus. It would be a fragmented, time-delayed mosaic. Signals from nearby stars would arrive as they were years ago. Signals from distant regions would arrive as they were tens of thousands of years ago. Some civilizations might have gone extinct long before their signals reached us. Others might not yet have begun transmitting at the moment we are receiving their earliest emissions. There is no now that spans the galaxy. Instead, there are layers of pasts stacked on top of each other, separated by vast distances and equally vast delays. The Milky Way is not a shared moment. It is a patchwork of histories. A useful way to think about this is not as a conversation, but as an archive. Imagine a library where every book was written in a different century, in a different language, and placed randomly on shelves that extend for thousands of kilometers. You're allowed to read only the books that happen to fall off the shelves and land within your reach. You do not know how many books there are, how many have been written, or how many are still being written. You only know what happens to arrive. That is what observing the galaxy is like. And when you look at it this way, the silence begins to feel less like a mystery and more like an expectation. Because the speed of light imposes a hard limit not just on how fast things can travel, but on how quickly information can propagate. It sets the pace at which cause and effect can unfold across the universe. It determines how long it takes for any signal, any message, any attempt at contact to move from one point to another. And when the distances involved are measured in thousands, millions, or billions of light years, that pace becomes glacial. The result is a universe in which connection is not impossible, but profoundly constrained. A universe in which signals take so long to travel that they lose coherence, lose relevance, or never arrive at all. A universe in which civilizations may rise, broadcast, and disappear without ever knowing that anyone else existed. In that context, the silence is no longer surprising. It is inevitable. It does not require self-destruction, or secrecy, or rarity. It does not require that civilizations hide or choose not to communicate. It emerges naturally from the combination of two facts. The universe is enormous, and the speed of light, though fast by human standards, is finite. The unsettling conclusion is that the cosmos may not be empty at all. It may be filled with life, with intelligence, with countless civilizations separated not just by space, but by time, each one existing in its own isolated bubble of causality, unable to reach beyond it in any meaningful way. The silence, then, is not the universe telling us that we are alone. It is the universe behaving exactly as physics predicts it should, and the most unsettling part is that there may be nothing we can do about it. Part 12. The Theories Reinterpreted. The standard explanations for the Fermi paradox are familiar territory for anyone who has spent time thinking about this question. Over the decades, scientists, philosophers, and writers have proposed an entire landscape of possibilities, some hopeful, some deeply unsettling, some bordering on existential dread. But when you re-examine these ideas through the lens of what we now understand about light-speed isolation, something subtle but profound happens. The explanations don't necessarily disappear, but they begin to lose their central role. They shift from being answers to being add-ons. Because once you account for the simple, unavoidable physics of how slow light really is across cosmic distances, the silence of the universe starts to look less like a mystery that needs solving, and more like the default state of reality. Take the Great Filter, for example, originally proposed by economist Robin Hanson in the late 1990s. The idea is both elegant and terrifying. Somewhere along the long chain from lifeless matter to a galaxy-spanning civilization, there is a step that is extraordinarily difficult, so difficult that almost nothing makes it through. This filter could lie behind us, in which case humanity is incredibly lucky. Maybe the emergence of complex cells was a near impossible event. Maybe the leap to multicellular life was the bottleneck. Maybe intelligence itself is vanishingly rare. If that's the case, then we are the exception, one of the few civilizations that manage to pass through a nearly insurmountable barrier. But there's a darker version of the same idea. The filter might not be behind us, it might be ahead. Civilizations might arise frequently, develop technology, and then reliably destroy themselves before they can expand into the galaxy. Nuclear war, environmental collapse, artificial intelligence gone wrong. Pick your mechanism. The result is the same. A universe where life appears, briefly shines, and then disappears before it can leave a lasting trace. It's a compelling framework. It gives the silence a cause. But when you introduce the constraint of the light-speed communication, the need for such a filter becomes less absolute. Even if civilizations are common, even if the galaxy is teeming with life, the physics of signal propagation ensures that most of that activity remains invisible to us. Signals take years, centuries, or millennia to travel between stars. By the time they arrive, they may be too weak to detect, too distorted to interpret, or too out of sync with our own moment in history to make sense of. In this sense, the speed of light acts as a kind of passive filter, not one that prevents civilizations from existing, but one that prevents their presence from being easily observed. You don't need a catastrophic bottleneck to explain the silence, if the evidence itself is naturally diluted to near zero by distance and time. A similar transformation happens when you look at the dark forest hypothesis, popularized by the science fiction of Liu Cixin but rooted in a kind of cold strategic logic. The premise is simple and chilling. In a universe where resources are finite and intentions are unknowable, every civilization is a potential threat. If you reveal your location, you risk being destroyed by a more advanced civilization that sees you as competition. The safest strategy, therefore, is silence. Hide. Stay quiet. Assume that everyone else is doing the same. At first glance, this seems like a plausible explanation for why we haven't heard anything. Maybe the universe isn't empty. Maybe it's just quiet on purpose. But again, the speed of light complicates the picture in a way that undermines the core premise. The fear in the dark forest scenario is that detection leads to immediate danger. But in reality, nothing travels faster than light. If a civilization detects a signal from 100 light-years away, any response, whether peaceful or hostile, cannot arrive for at least a century. More realistically, if travel is involved, it could take thousands of years. This changes the strategic landscape completely. The threat is still real in principle, but it operates on timescales that are almost incomprehensible from a human perspective. A civilization that sends out a signal today might be entirely transformed or extinct by the time any response arrives. The idea of maintaining a consistent long-term strategy of silence over centuries or millennia becomes difficult to sustain. Distrust loses its immediacy when cause and effect are separated by such vast stretches of time. In a strange way, the speed of light acts as a built-in buffer, reducing the urgency that would otherwise drive civilizations into hiding. The forest may still be dark, but the distance between the trees is so immense that the danger feels less immediate, less actionable. The zoo hypothesis offers a very different kind of explanation, one that replaces fear with intention. First proposed by MIT radio astronomer John Ball in 1973, it suggests that advanced civilizations are aware of us, but have chosen not to interfere. Earth, in this view, is something like a protected reserve, a place to be observed but not disturbed. The silence is not an accident, it is a policy. There is something almost comforting about this idea. It implies that we are not alone, that there are beings out there with the capability to reach us, but who have decided to let us develop on our own terms. It frames the universe as a place of quiet guardianship, rather than indifferent emptiness. But once again, light-speed isolation introduces a problem that is hard to ignore. Observation across interstellar distances is not observation in real time. It is observation of the past. A civilization watching Earth from 50 light-years away is seeing us as we were 50 years ago. From 100 light-years away, they are seeing the early 20th century. Any decision they make based on that information is already outdated by the time they could act on it. And any action they take, whether it is to intervene, to communicate, or to continue observing, would take decades or centuries to reach us. This creates a kind of temporal disconnect that undermines the idea of active, responsive oversight. A zookeeper, operating under these constraints, is not managing a living, evolving system in real time. They are watching a delayed recording, making decisions based on incomplete and outdated information. The notion of a coordinated, galaxy-wide policy of non-interference becomes increasingly difficult to reconcile with the reality that every participant is effectively out of sync with every other. Then there is the rare earth hypothesis, developed by paleontologist Peter Ward and astronomer Donald Brownlee. This idea takes a different approach altogether. Instead of focusing on what civilizations do, it focuses on how unlikely they are to arise in the first place. According to this view, while simple microbial life might be common, the conditions required for complex intelligent life are extraordinarily rare. Earth, with its stable star, protective magnetic field, plate tectonics, large moon, and long-term climate stability, might be an outlier. The silence in this case is not the result of distance or behavior, it is the result of rarity. There simply aren't many civilizations to hear from. This is a sobering possibility, and one that cannot be dismissed. But even here, the speed of the light complicates our ability to draw conclusions, because from our perspective, there is no clear observational difference between a galaxy that is truly empty and a galaxy that is full of life, but separated by such vast distances and delays that its signals have not yet reached us. Both scenarios produce the same observable outcome: silence. In other words, light-speed isolation creates an observational ambiguity. It limits not only our ability to detect other civilizations, but also our ability to determine whether they exist at all. Rare Earth may be true, or it may not be, but the constraints imposed by the speed of light ensure that we cannot easily tell the difference. What emerges from all of these reinterpretations is a single, unifying insight. Whatever else is true about life in the universe, whether it is common or rare, cooperative or hostile, short-lived or enduring, the speed of light imposes a structural isolation that none of these factors can overcome. It is not just one variable among many. It is the framework within which all other variables operate. Even in the most optimistic scenario imaginable, a galaxy filled with civilizations, all of them technologically advanced, all of them stable, all of them actively broadcasting, the result would not be a vibrant interconnected network. It would be something far stranger. A fragmented, asynchronous patchwork of signals, each one representing a different time, a different place, a different stage of development. Some would arrive too early to be recognized, others too late to be relevant. Many would never arrive at all. The galaxy would not feel alive in the way we intuitively expect. It would feel quiet, not because nothing is happening, but because everything is happening too far apart, too slowly, and too out of sync to form a coherent whole. The theories are fascinating. They give us narratives, possibilities, ways to imagine our place in the cosmos. But when you strip everything back to the underlying physics, a simpler explanation emerges, one that does not depend on speculation about alien behavior or unlikely evolutionary paths. The speed of light, measured against the scale of the universe, is simply too slow to allow for meaningful connection, and that may be enough to explain the silence all by itself. Part 13. The Expansion Trap. Here is where it gets worse. And it is worth slowing down and being precise here, because this is not just another layer of difficulty. This is one of the strangest, most counterintuitive, and genuinely unsettling features of modern cosmology. It takes everything we have already established about the speed of light as a limiting factor, and then quietly makes the situation far more extreme. We begin with something that sounds familiar. The universe is expanding. This is not speculation. It is one of the most firmly established observations in astrophysics, first confirmed by Edwin Hubble in the 1920s. By measuring the light from distant galaxies, Hubble discovered that they are moving away from us, and crucially, that the farther away a galaxy is, the faster it appears to be receding. This relationship, now called Hubble's law, revealed that the universe is not static. It is dynamic. It is changing. It is growing. But even that description, galaxies moving away, is slightly misleading. It suggests motion through space, as if galaxies are like rockets flying outward into a pre-existing void. That is not what is happening. The deeper, more accurate picture is harder to visualize. Space itself is expanding. The distances between galaxies are increasing not because they are flying apart, but because the fabric that separates them is stretching. The analogy often used is that of dots on the surface of a balloon. As you inflate the balloon, the dots move away from each other, but they are not moving across the surface. They are staying in place relative to the surface itself. It is the surface, the space between them, that is growing. Every dot sees every other dot receding, and the farther apart two dots are, the faster that separation increases. So far, this is strange but manageable. It fits within our intuition once we adjust to the idea that space can stretch. But now comes the part that breaks intuition again. Some galaxies are receding from us faster than the speed of light. At first hearing, this sounds like a direct violation of everything we know about physics. We have just spent all this time establishing that the speed of light is the ultimate limit. Nothing can move faster than light. That is one of the central pillars of Einstein's theory of relativity. So how can anything, let alone entire galaxies, be moving away faster than that? The answer lies in a subtle but crucial distinction. The speed limit imposed by relativity applies to motion through space. It does not apply to the expansion of space itself. When galaxies appear to recede faster than light, they are not breaking the rules by moving through space at impossible speeds. Instead, the space between us and them is expanding, and that expansion can occur at a rate that effectively increases the distance faster than light can traverse it. There is no violation here. Einstein's equations actually allow for this. It is not a loophole or a trick. It is a natural consequence of how space-time behaves on the larger scales. And this leads us to a boundary that is both mathematically precise and conceptually unsettling: the Hubble sphere. The Hubble sphere is defined as the distance at which the recession velocity of galaxies equals the speed of light. Right now, that distance is roughly 14 billion light-years from Earth. Inside this sphere, galaxies are receding from us at speeds less than light. In principle, light emitted from those galaxies can still make its way toward us. It may take billions of years, but it can get here. Outside the Hubble sphere, something very different happens. Galaxies beyond this boundary are receding from us faster than light, not through motion, but through expansion. And because of that, any light they emit toward us is effectively trying to swim upstream in a river that is flowing away faster than it can move forward. The photons are still travelling at the speed of light locally, obeying all the rules of physics. But the space they are moving through is stretching so rapidly that they never make net progress toward us. Their signals will never arrive. Not in a billion years, not in a trillion years, not ever. Those galaxies are, in the most complete physical sense, unreachable. This is not a limitation of technology. It is not something we can overcome with better telescopes, more powerful transmitters, or faster spacecraft. It is not even a limitation in the sense we usually think of, like a barrier we might one day break through. It is a structural feature of the universe itself, a region beyond which information simply cannot propagate back to us, no matter what we do. And yet, paradoxically, we can still see some of these galaxies, because the universe has not always been expanding at the same rate. Light emitted from distant galaxies billions of years ago, when they were closer and the expansion was slower, has had time to reach us. That is why we can observe objects that are now far beyond the Hubble sphere. We are seeing them as they were in the distant past, but any light they emit now will never reach us. They have crossed a threshold beyond which they are causally disconnected from our future. This brings us to an even more important concept: the cosmological event horizon. If the Hubble sphere marks the boundary where recession speed equals the speed of light, the event horizon marks something deeper. It is the boundary beyond which events can never influence us no matter how long we wait. It defines the true limits of our observable, and more importantly our reachable universe, and that boundary is not fixed. Because the expansion of the universe is not just continuing, it is accelerating. The force driving this acceleration is something we call dark energy. It is not fully understood. We do not know exactly what it is or why it exists, but we know it is real because we can measure its effects. Observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe all point to the same conclusion. The expansion of space is speeding up. This changes everything, because it means that the rate at which galaxies recede from us is increasing over time. Galaxies that are currently within our reach may not remain so indefinitely. As the expansion accelerates, more and more regions of the universe cross the threshold where their recession velocity exceeds the speed of light. They slip beyond the horizon. They become permanently inaccessible. What this means, in practical terms, is deeply counterintuitive. The universe as a whole is getting larger, the total amount of space is increasing, but the portion of the universe that we can ever interact with, that we can ever send signals to or receive signals from, is shrinking. We are not expanding into the cosmos is expanding away from us, and it is taking more and more of itself beyond our reach with every passing billion years. This is what we might call the expansion trap. We exist inside a kind of cosmic bubble, a region of space within which signals can still, in principle, travel back and forth. But that bubble is not growing with the universe. It is, in a very real sense, contracting relative to the total size of the cosmos, not on human timescales, not on the scale of civilizations or even species, but on the scale that matters for any truly long-term view of the future. If you imagine an advanced civilization capable of surviving for billions or trillions of years, this is the environment it would inhabit. A universe where more and more of the cosmos is slipping away, where distant galaxies fade beyond reach, where the night sky gradually empties as once visible structures redshift and disappear. The walls are not static, they are moving inward. And this is where the connection to the speed of light becomes unavoidable again, because the expansion of the universe does not change the speed of light. It does not relax the limit. It does not offer a workaround. If anything, it makes the consequences of that limit more severe. The speed of light remains the maximum rate at which information can travel, but the distance that information must cross is increasing, and in some cases increasing faster than light can compensate for. So the same constraint that already made interstellar communication difficult, that already made galactic civilization improbable, now combines with cosmic expansion to create something even more restrictive. Not just isolation, but growing isolation. Not just a prison, but a prison whose walls are slowly closing in. It is important to be clear about the timescales here. This is not something that affects daily life, or even the long-term trajectory of human civilization as we currently imagine it. The galaxies around us will remain visible for billions of years. The local group, including the Andromeda galaxy, is gravitationally bound and will eventually merge with our own. But beyond that local neighborhood, the universe is slowly disappearing. If you project far enough into the future, tens or hundreds of billions of years, the observable universe for any civilization that still exists will be dramatically smaller. Distant galaxies will no longer be visible. The cosmic microwave background will fade. The evidence of the Big Bang itself may become undetectable. Future astronomers, living in that distant era, might look out at a much emptier sky and conclude that the universe consists only of their local cluster of galaxies, unaware of the vast cosmos that once existed beyond their horizon. In that sense, we are living at a kind of privileged moment in cosmic history, a time when the universe is still visible in its large-scale structure, a time when we can still, in principle, detect signals from distant regions, a time when the full scope of the cosmos is not yet hidden from view. But that window is temporary, and the deeper implication, the one that ties everything together, is this. The speed of light does not just limit what we can do, it defines what is possible at all. And when you combine that limit with an expanding universe, you get a cosmos in which connection is not just difficult, but fundamentally constrained in a way that becomes more severe over time. The expansion trap is not a speculative idea. It is not a hypothesis waiting to be tested. It is a direct consequence of observations we have already made and theories that have been confirmed to extraordinary precision. And it leaves us with a final unsettling realization. The universe is not only vast and slow, it is becoming, with every passing moment, more unreachable. Part 14. The event horizon of reality. The observable universe, the vast sphere of everything whose light has had enough time to reach us since the beginning of cosmic history, stretches out to a radius of approximately 46.5 billion light-years. At first glance, that number feels wrong. If the universe is about 13.8 billion years old, you might expect the most distant light we can see to have travelled 13.8 billion light-years to get here. That would be the intuitive answer. But intuition breaks down once you account for the fact that the universe has not been sitting still while that light was in transit. Space itself has been expanding the entire time, so the light we observe today from the most distant regions did not travel across a fixed, static distance. It began its journey when the universe was much smaller, and as it moved toward us, the space between us and its source stretched, carrying that source farther and farther away. By the time that ancient light finally arrives, the region it came from is no longer 13 billion light-years away. It is now over 46 billion light-years distant. One of the most striking examples of this comes from the cosmic microwave background, the oldest light we can observe. It was emitted when the universe was only about 380,000 years old, when matter and radiation first decoupled and photons were free to travel. That light has been moving toward us for nearly the entire history of the universe, and yet the regions that emitted it are now more than 46 billion light-years away due to cosmic expansion. This leads to a subtle but important realization. The observable universe is centered on us, extending in every direction equally, not because we occupy a special place in the cosmos, but because observation itself is centered on the observer. Any galaxy, anywhere in the universe, would see itself at the center of its own observable sphere. This is a consequence of how light travels and how expansion works, not a sign of cosmic privilege. But here is where the distinction becomes critical. Observable does not mean accessible. There is another boundary, less widely understood but far more consequential, called the cosmological event horizon. While the observable universe defines what we can see, the event horizon defines what we can ever interact with. It marks the limit of what we can reach, influence, or receive signals from in the future, given the accelerating expansion of space. And that boundary is much closer. Right now, the cosmological event horizon sits at roughly 16 billion light-years from Earth. Anything beyond that distance is already beyond our permanent reach, not in the distant future, not after billions of years of technological advancement, right now. The reason comes back to the same phenomenon we explored earlier. Space is expanding, and it is doing so at an accelerating rate. Beyond a certain distance, the expansion of space between us and a distant galaxy is occurring so rapidly that even light, travelling at the maximum speed allowed by physics, cannot overcome it. Any signal we send toward those regions will be carried away faster than it can progress. Any signal they emit today will never reach us. Those regions are causally disconnected from our future. They still exist. They are still part of the universe. But they are separated from us by a kind of one-way boundary that no information can cross. This is where the numbers become difficult to fully absorb. Current estimates suggest that approximately 94% of the galaxies within the observable universe are already beyond this cosmological event horizon. 94%. That means that out of all the galaxies whose ancient light we can see in our telescopes, only a small fraction remain within a region where any future interaction is even theoretically possible. The rest are already gone, in the only sense that ultimately matters, not destroyed, not erased, but separated from us by a distance that no signal, no spacecraft, no form of communication can ever bridge. If we take the widely cited estimate of roughly 2 trillion galaxies in the observable universe, based on deep surveys such as those led by astronomer Christopher Consulis and his colleagues, the implication becomes staggering. Roughly 1,880 billion of those galaxies are already beyond our reach. Entire island universes, each containing billions or hundreds of billions of stars, each potentially hosting countless planets, and perhaps forms of life or intelligence, are permanently inaccessible to us. We can see them. We can study the light they emitted billions of years ago, but we will never touch them. We will never send a signal that arrives. We will never receive a reply to anything we transmit today. They are like images frozen in time, visible but untouchable, like a face seen through a window that will never open. This is where the emotional weight of the physics begins to settle in. We tend to think of the universe as something that is opening up over time, becoming more knowable as our technology improves. There is a sense of expansion, of progress, of eventually reaching out and exploring more and more of what is out there. But the reality, on the larger scales, is almost the opposite. The universe is becoming less accessible as it ages. The key moment in this process occurred several billion years ago, when the expansion of the universe transitioned from slowing down under the influence of gravity to speeding up under the influence of dark energy. This transition happened roughly 5 billion years ago. Since then, the rate at which space expands has been increasing, and with it, the rate at which distant galaxies recede from us. From that moment onward, the accessible universe began to shrink. Not in physical size, but in terms of what could ever be reached or influenced. Every billion years that passes, more galaxies cross the cosmological event horizon. More regions of space become permanently disconnected. More potential neighbours slip beyond the boundary where any form of contact is possible. This is not a sudden event. It is not a dramatic collapse. It is a slow, steady process, unfolding over cosmic timescales. But it is relentless. Imagine marking a set of galaxies just at the edge of reachability today. In 1 billion years, some of them will no longer be reachable. In 10 billion years, far more will have slipped beyond the horizon. Given enough time, the only galaxies that remain within reach will be those that are gravitationally bound to us, primarily the members of our local group. Everything else will fade away. If we project this far enough into the future, the implications become almost surreal. Civilizations that might arise tens or hundreds of billions of years from now will not see the same universe we see. Their night sky will be darker, emptier. The distant galaxies we observe today will have redshifted beyond detectability. Their light stretched to wavelengths so long and so faint that they effectively disappear. Even the evidence for the Big Bang itself may become inaccessible to them. They may look out into the cosmos and conclude that the universe consists only of their local cluster of galaxies, unaware that a vast cosmic web once extended far beyond their horizon. The larger structure of the universe, the very idea of a universe filled with trillions of galaxies, could become unknowable to future observers. In that sense, we exist at a uniquely privileged moment. We live early enough in cosmic history to see the large-scale structure of the universe. We can observe galaxies billions of light-years away. We can detect the cosmic microwave background. We can reconstruct the history of cosmic expansion. We have access, at least observationally, to a vast portion of the cosmos. But even for us, that access is partial, because what we see is not what is, it is what was. And even more importantly, much of what we see is already beyond any possibility of future interaction. This reframes the entire question of cosmic connection in a profound way. When we ask why we have not heard from other civilizations, we often imagine a static universe, where distances are fixed, and the only variables are technological or biological. Maybe civilizations are rare. Maybe they destroy themselves. Maybe they choose not to communicate. But when you factor in the cosmological event horizon, a different picture emerges. Even if the universe is full of life, even if civilizations arise frequently across billions of galaxies, the majority of them are already beyond our reach. Not because they are hiding, not because they are silent, but because the structure of space-time itself prevents any exchange of information. The silence is not just a mystery of behavior, it is a consequence of geometry and expansion. We are, in a very real sense, already late to the cosmic conversation. The window during which different regions of the universe could have meaningfully interacted has been narrowing for billions of years. Whatever connections might have been possible across vast distances in the early universe are becoming less and less feasible as time goes on. The universe is not becoming more interconnected. It is fragmenting, slowly, irreversibly, and in a way that no technology can reverse. And through all of this, one constant remains: the speed of light. It does not change. It does not adapt. It does not increase to compensate for the growing distances. It remains fixed. The ultimate speed limit, the maximum rate at which any signal can travel. In a static universe that would already impose severe constraints, in an expanding universe, it becomes something more. It becomes the mechanism that enforces separation, the lock on the door. Because no matter how advanced a civilization becomes, no matter what technologies it develops, it cannot exceed that limit. And when the distances themselves are growing faster than that limit allows signals to cross, the result is inevitable. A universe that is visible but not reachable. A cosmos filled with galaxies, most of which are already beyond any possible relationship we could form with them, and a future in which that isolation only deepens. We are fortunate in a cosmic sense to live at a time when the universe still reveals so much of itself. We can see 2 trillion galaxies. We can study their light. We can map the structure of the cosmos on the larger scales. But even now, most of that universe is already beyond our grasp, and for any observers who come after us, billions of years in the future, the situation will be even more extreme. They will inherit a smaller observable universe, a tighter horizon, a lonelier sky. They will live in a cosmos that has, in a very real way, forgotten the rest of itself. And the reason for that ultimately will trace back to the same simple fact we started with. The speed of light is the fastest thing in the universe, and it is nowhere near fast enough. Part 15. The Final Realization. We began with a number. 299,792,458 meters per second. The speed of light. The fastest anything can go. The ultimate limit of motion, of information transfer, of causality itself. And we spent this entire journey treating that number as if it were almost the problem, as if the universe had given us something close to adequate and just fallen a little short, as if the speed of light were almost fast enough and we were just unlucky that the universe turned out to be so big. But I want to suggest a different way to see it, and it is the frame that has been building across everything we have covered. The speed of a light is not an almost adequate solution to the problem of cosmic distances. It is the structural feature of reality that guarantees isolation. It is not a limitation imposed from outside. It is built into the equations, into the nature of space-time itself, into the relationship between energy, mass, and motion that Einstein described. The universe is not big in spite of the speed of light. The universe is effectively isolated because of it. The scale and the speed limit together do not produce a universe that is hard to navigate. They produce a universe where navigation, in any meaningful sense, may be impossible across the distances that actually separate things. Return to Fermi's question, where is everybody? And look at what we now know. The nearest star is over 4 light-years away, an 8.5-year communication round trip at best. The galaxy is 100,000 light-years across. A round-trip communication with the far side takes 200,000 years, longer than our species has existed. 94% of observable galaxies are already beyond any possible reach, already past the event horizon, already gone in the practical sense that matters. And the expansion of space is accelerating, pulling more of the universe past that threshold every billion years. Given all of that, given distances that are staggering, a speed limit that is absolute, an expansion that is accelerating, and communication delays that exceed the lifespans of civilizations, the silence is not the mystery. The silence is the prediction. The silence is what physics requires. If you model a universe with these parameters, you do not predict a cosmos full of chatter and connection and signal-sharing civilizations in regular contact with each other. You predict exactly what we observe. Isolated islands of intelligence, each looking outward, each unable to reach the others, each broadcasting into a void that is not truly empty, but is too large and too fast expanding to bridge. People sometimes ask whether we might be alone in the universe. It is a haunting question because the loneliness implied by a truly empty cosmos, 2 trillion galaxies, billions of stars each, and only us, is almost too large to hold in your mind. But here is what I find in some ways more philosophically interesting about what we have uncovered today. The alternative, a universe full of life, full of intelligence, full of civilizations that have existed for millions of years, does not actually solve the loneliness problem. Because if the speed of light is the lock, then it does not matter how many civilizations are out there. They are as unreachable as if they did not exist. A universe full of life, separated by physics into permanent isolation, is not meaningfully different from the perspective of any single civilization, from a universe that is empty. The company is there. The connection is not. There is something here that cuts close to questions that are not purely scientific. Questions about what it means to reach out, to want to be known, to hope that the darkness is not as absolute as the numbers suggest. Every civilization that has ever evolved enough to look up has probably done what we do. They have probably felt the same pull, the same curiosity, the same hope, the same ache to know that something else is out there. And if they looked at the physics as carefully as we have today, they arrived at the same conclusion. The universe is full, and the universe is unreachable. Every civilization is an island, and the ocean between them is made of light years, and the fastest boat physics allows is still too slow to matter. But here is what I keep coming back to. We are looking. Despite all of this, despite everything the math says about the futility of contact, despite the event horizons and the expansion and the 100,000-year round trips across our own galaxy, we are still pointing telescopes at the sky and listening. We are still transmitting. We are still asking the question. Maybe that impulse, that irreducible refusal to accept isolation without at least trying, is itself a signature. Maybe every civilization that reaches this understanding sends one more signal anyway, not because they expect a reply in their lifetime, but because the act of reaching matters even when reaching is impossible. The speed of light is not just a limit. It is not just a wall. It is not just a barrier between here and everywhere else. It is the architecture of the universe itself, the physical law that defines what contact is possible and what connection means across the cosmos. And it is, in the most complete sense of the word, a lock. The universe is the room. We're inside it. We can see through the windows, and the fastest key physics allows us to turn still moves too slowly to open the door. We are here. Something else may be out there, and the space between us is measured in years of light, years of silence, years of signals crossing in the dark that will never arrive in time to matter. That is the terrifying truth about how slow the speed of light really is.